In the previous 5 items, I have treated steady climbing and descending flight. Steady climb or descent performance means that the airspeed is constant. When the aircraft is accelerating or decelerating, some more advanced maneuvers and trajectories can be performed. But that is an advanced topic, not treated in this course. If you are provided with basic aerodynamic and propulsion system data of an aircraft, so the lift-drag polar and the maximum propulsive force as a function of airspeed, you should now be able to calculate the climb and descent performance. To be more specific, you should be able to calculate the maximum climb angle, the maximum rate of climb, the minimum descent angle, the minimum rate of descent, and also the climb performance for a given thrust setting, so anywhere between maximum and minimum, and the thrust setting for a given climb angle or rate. Climb rate and climb angle can be visualized with the airspeed vector. Now the angle this vector makes with the horizon is the climb angle. The vertical component is in fact the climb rate. Now remember that the condition for a maximum climb angle is not the same as the condition for maximum climb rate. In order to perform the calculations, you require the equations of motion for steady symmetric flight. Now, it may be confusing in these equations to see lift is equal to weight here. The full equation for steady symmetric flight perpendicular to the airspeed vector actually has a cosine gamma term as well. However, since the angles are always quite small, less than 20 degrees, the cosine term in fact approaches 1. And thus we remove it from the equation to make our life a bit easier. Now this second equation can be used to calculate climb angle if thrust and drag are known. If we are, on the other hand, interested to calculate the climb rate, we should multiply this second equation with the airspeed. Now when you do that, we obtain the power equation. This equation has rate of climb as one of the variables, but in fact it is derived from the second equation of motion. So nothing new here. So when power available and power required are known, you can actually calculate rate of climb. Now a very nice way of summarizing the performance is the performance diagram. In this diagram, aerodynamic drag and the propulsive force are sketched as a function of airspeed. Now if we assume to have an idealized jet engine with constant maximum thrust as a function of airspeed, we can derive that the condition for maximum climb angle occurs at the airspeed for minimum drag. At the same time, this point is also optimum for minimum descent angle, in case there is no engine power. We can also make a performance diagram with power on the y-axis instead of a force. If we assume to have an idealized propeller aircraft with maximum power available independent of airspeed, we can derive in this diagram that the condition for maximum rate of climb occurs at the airspeed for minimum power required. At the same time, this point is ideal to obtain minimum rate of descent angle in case there is no engine power. It is quite important to realize that these diagrams are applicable for one specific altitude or air density and one specific aircraft weight. Now, what will happen to the climb performance if an aircraft goes up in the atmosphere? Will it improve or get worse? Now, this will be the topic of the next item. I will then address the effect of altitude on aircraft performance.